In the next section, we're going to show how the rational numbers are not sufficient to support all of mathematics. Q, the rational numbers, is not sufficient to support all of mathematics. Here are some examples. X squared equals 2, x cubed equals 5, x squared equals 10. Not one of them has a solution in the rational numbers. Theorem 0.18 is going to describe a very, very specific rational number that is not rational. There is no rational number whose square is 2, and that's what we're going to prove. Let's let A over B be a rational number in reduced form. By reduced form, one way of writing that is that the greatest common divisor of A and B is equal to 1. They are relatively prime numbers. So we've done all the canceling. This is a simplified, reduced fraction. Now, we're going to do this proof by contradiction. I'm going to say, to the contrary, suppose A over B squared is equal to 2. Let's see. To the contrary, because I know I'm going to reach a contradiction, because I know that there is no rational number I can square to get 2. To the contrary, suppose that A over B squared is equal to 2. And what we'll do is we will continue with our algebra, and we're going to reach a contradiction, which something contradicting an assumption from the above. And that means then that our statement, this is false. Suppose A over B squared equals 2. If we can reach a contradiction because of that, then that statement is false. All right, thus, if that's the case, we can see the following. Well, let's multiply this out. A over B times A over B, that's equal to 2. And that implies that A squared is equal to 2B squared. Well, by the definition of an even number, that tells us that A squared is even, because A squared is 2 times another integer. Well, if A squared is even, that means A is even. And I'll assume we know that to be true. Essentially, to prove that A squared even implies A is even, a very simple proof would be to use the proof by contradiction, by contrapositive. If A is odd, then A squared is odd, and that's a very easy statement to prove. Okay, well, if A is even, that means A is equal to 2k for some integer k. And now we're going to do a little bit of substitution. That implies from this step up here, the fact that A equals 2k and A squared is 2b squared, I can say that A squared, this is A being squared, is equal to 2b squared. And that implies that by dividing both sides by 2, I get 2k squared equals b squared. Because upstairs, this was a 4k squared. If I divide it by 2, I get 2k squared. Divide this by 2, the 2 goes away. And that tells us that b squared is even. Because b squared is 2 times an integer. And that tells us that b is even. Now, can you see where we get the contradiction? I'd like to continue down at the bottom. Maybe I will put just a few more words up here. But A and B are both even. From here and here implies A over B not in reduced form. Is that how I stated it, in reduced form? That's our contradiction. We started off with A over B in reduced form, and if we assume that A over B squared equals 2, we reach a contradiction that A and B are not in reduced form, like we assumed or we supposed from the very beginning. Therefore, there is no rational number whose square is 2.